Hi everyone, I hope you're doing so well. Obviously I miss you guys a ton and would rather be teaching you guys in person. It'd be awesome to see your faces, but unfortunately we don't get to, so this will be the next best thing. I'm actually restarting this video for the third time. I've been having some technical difficulties, but hopefully third time's the charm. We'll have to see. So if you remember before break, we talked a lot about covalent bonding. So we're in our unit on bonding, and there's three major sections of that: ionic, covalent, and metallic. We spent a long time talking about covalent bonding, Lewis dot diagrams, double bonds, triple bonds, the VSEPR theory to get the geometry, hybridization, and so forth. So we've really done quite a complete review of covalent bonding, but today we need to talk a little bit about both ionic bonding and metallic bonding. So ionic bonding occurs between a metal and a nonmetal and always involves a transfer of electrons. So like I just said, occurs between a metal and a nonmetal. And this is because metals have a low ionization energy. Remember that ionization energy is the energy required to remove an electron. Something like sodium, which just has one valence electron, has a pretty low ionization energy because if it were to lose this valence electron, it achieves that noble gas-like configuration, which is always energetically favorable. So metals tend to have low ionization energies. On the other hand, nonmetals, something like chlorine, which has 7 valence electrons, has a high electron affinity. Now, electron affinity is how much an atom wants to gain an electron. So obviously it makes sense, since chlorine has 7 valence electrons, it wants to gain that 8th valence electron so that it achieves that noble gas-like configuration. So because metals have a low ionization energy and nonmetals have a high electron affinity, ionic bonding occurs by transferring an electron from a metal to a nonmetal. So let's take a look at what that looks like. Here, just the example I was doing: sodium, 1 valence electron; chlorine, 7 valence electrons. What happens is there's no sharing of electrons like there was in covalent bonding. Sodium actually has such a low ionization energy and chlorine has such a high electron affinity that sodium just transfers the electron to chlorine. That electron actually moves over, and therefore we get NaCl. Na actually forms that positive 1 ion, and Cl actually forms that negative 1 ion. Overall, sodium chloride is neutral, but it's composed of the positive and negative ions. We can take a look at something like aluminum bromide. Aluminum has 3 valence electrons, and bromine has 7, just like chlorine. And what ends up happening here is aluminum, with the low ionization energy, transfers 1 to bromine. This bromine now achieves that noble gas-like configuration, right? The 8 valence electrons on the outer shell. So that means the next electron isn't going to go to that same bromine. Instead, that aluminum will find a second bromine to which it can donate, and then a third bromine to which it can donate. And this is why aluminum bromide ends up being AlBr3. And that's because aluminum becomes a +3 ion, or I should really say 3+ ion. And bromine is a -1 ion, or a 1- ion, but there are 3 of them. So it's important to realize that bromine doesn't become a 3- ion. It becomes 3 1- ions. Okay, here's calcium oxide. Calcium has 2 valence electrons. Oxygen has 6 valence electrons. Both of these will transfer over, and we will get calcium oxide. This would be our 2+ ion and this would be our 2- ion. Last one, strontium, 2 valence electrons, chlorine, 7 valence electrons, transfer 1, chlorine achieves that octet, so it's not going to accept a second one, so strontium will look around for another chlorine, donate there, SrCl2, that's a 2+ ion because strontium lost 2 electrons, and I have 2 1- ions because chlorine gained an electron. Okay, so that's essentially how ionic bonding works. Ionic substances tend to have similar properties. They're brittle, they have high melting points, they're usually crystalline, which means they're neatly organized atoms that are tightly packed in. So when we say that they're crystalline, it means all the atoms are nicely organized and tightly packed into solids, essentially. Sometimes they use this term lattice, which we will talk about in a second as well. And crystals, of course, can be cleaved, which means they can be broken apart along smooth, flat surfaces. So when you analyze crystalline structures, you realize that you can break them on certain planes, which means that they're cleaved. That actually is a little bit beyond the scope of our course, but it is something that you would learn about if you went on to take chemistry in college. You would get to a course called inorganic chemistry where they really look at all the different types of crystalline structures and how they can be cleaved. So I just mention it here, but I don't think it's something that we'll get asked about in our AP exam. But it is important to know that ionic solids tend to have this crystal lattice structure. Okay. Now we'll go back to the idea of the lattice structure in just a moment, but let's talk about the energy of ionic bonds. So the formation of an ionic substance is always exothermic, okay? And you could confirm this by looking at Appendix C in your book if you wanted. We looked at that appendix during our thermo unit, and we looked at enthalpies of formation. And if you look up the enthalpy of formation for any ionic solid, you'll find that the delta H is negative, which means it's an exothermic process. So how is this process exothermic? Well, when we think about it, we think about losing an electron. So remember that it takes energy to remove an electron. So for example, from sodium, it will require energy to remove this electron. And that will be an endothermic process because it takes energy. So the delta H for that process would be positive. Atoms give off energy when they gain electrons. So when the chlorine gains that 1 electron, right, like an electron is coming in, that process is going to be exothermic, which is going to be negative. So one would think that to get the delta H for this whole process, we just add up this delta H and this delta H. But if we think about that, that won't always yield a negative value. So that wouldn't mean that every substance has this exothermic process happening when the ionic substance is formed, because depending on the magnitude of the delta H values, the overall delta H could be positive or negative. So how can we say that the formation of an ionic substance is always exothermic? Well, it turns out by just adding up the 2 delta H's of removing and gaining the electron, that wouldn't always yield an exothermic reaction. But that's because that is the correct math if the Na ion and the Cl ion were infinitely far apart from each other. So if everything was acting completely independently, sure, we would go ahead and do exactly what we were talking about. Find the delta H of removing the electron, find the delta H of gaining the electron, adding it up. Maybe it would be positive, maybe it would be negative, meaning maybe endothermic, maybe exothermic. But that would assume that the ions are acting independently, when in reality, oppositely charged ions, the Na plus and the Cl minus, are going to be attracted to each other. And because they're attracted to each other, they're going to form a lattice, okay? Remember, whenever bonds form, meaning those ions are attracted to each other, energy is given off. And therefore, this is an exothermic process. So it's important for you to remember that the formation of an ionic solid is always going to be exothermic. And then what I just talked about is the reasoning it is exothermic. And that's essentially that the ions get attracted to each other. And since the ions get attracted to each other, bonds form and energy is given off. So I said the word lattice earlier, right? It says like attracted to each other and form a lattice. And so what exactly is a lattice? A lattice is a geometric arrangement of the points in space at which the atoms, molecules, or ions of a crystal occur. So that's the official definition. In other words, the lattice is just how the atoms and ions are arranged to form a crystal. So here is the crystal structure or the lattice of NaCl. Now, it is important that we can look at something like this and think, okay, well, Na and Cl, these are Na ions and Cl ions, which ones are smaller and which ones are larger. So we would need to look at a periodic table to see that our sodium ion and our chlorine ion, I actually do need to look at a periodic table really quick. Let me see if I can figure out how to do that. I know I have one in here somewhere. Let me do a little bit of quick moving through. We're looking at the sodium ion and the chlorine ion. Here we go. Here's a periodic table. So chlorine ion essentially adopts a look like argon, and the sodium ion is going to adopt a look of neon. So if I'm comparing neon and argon, neon's going to be smaller and argon's going to be bigger. So I know that my sodium ion is the smaller one and my chlorine ion is the bigger one. Awesome. So if I go back here to where I was, here we go. I know that the sodium ion ends up being smaller because it looks kind of like neon. So that's going to be the purple ones. And the chlorine ion is the larger one. It adopted a argon-like configuration. So that's going to be the chlorine. So it's important to think about that when you see a structure like this. Okay, so this is the crystal lattice of NaCl, and lattice is just like the crystal formation, how the atoms or ions are arranged. Really ions if we're talking about an ionic structure. So a lattice is going to form by maximizing the attractive forces between the positive and the negative ion and minimizing the repulsive forces. So if we look back here, the chlorines want to be as far away from other chlorines as they can be so that they're not repelling each other. The sodium ions want to be as far away from each other so that they're not repelling each other. And we want to maximize the plus and the minus attraction that's happening. So for sodium chloride, this type of crystal does that the best. The chlorine ions are as far away as possible. The sodium ions are as far away as possible, but the sodium and chlorine are getting that maximum attractive force. So lattices will form to maximize the attractive forces between the positive and negative ions and minimize the repulsive forces. Now, remember that like molecular geometry, a lattice is always a 3D structure. The picture that we looked at before showed us that, which is nice. But like in terms of what will the lattice actually look like, there are tons of different types of lattices that can be formed for an ionic solid, and each has super unique properties. And like I mentioned earlier, if you were to go on to study chemistry in college, you'll take a whole class that talks about all these different types of lattices. I think lattices is a word. So here's a quick chart of them. We've got like cubic, face-centered, cubic, body-centered. You'll see like all these different options, right? This is going to be beyond the scope of our course, so you don't need to be able to identify what kind of lattice something has, but you do want to know that ionic solids form crystal structures known as lattices or as a lattice, and that different types of lattices have different properties. Okay, and so back to that energy idea of like ionic solids giving off energy, we have something called lattice energy. So the lattice energy is a measure of how much stabilization is given by arranging the ions in a solid. Remember, the ions are arranging themselves to be as stable as possible, maximizing the attractive force and decreasing the repulsive force. And so the lattice energy is the measure of how much stabilization is actually given. Okay. So the other way to think about lattice energy is the energy required to completely separate 1 mole of a solid ionic compound into its gases. So while lattice energy is the measure of how much stabilization is given, really, like experimentally, the way they determine the lattice energy is they figure out how much energy is required to separate 1 mole of the compound into its elements. So that would be like taking NaCl and breaking it into the sodium and the chlorine ions, right? And so the higher the lattice energy, the more stabilization is provided by becoming a lattice, okay? So mostly the question we get about lattice energy is like, which has the higher lattice energy? Lattice energy is dependent on the charges of the ions, their sizes, and their arrangement. Okay. Essentially, we look at the electrostatic force, which can be defined by this equation right here. The electrostatic force is something that we looked at earlier as well, and Q1 and Q2 are the charges of the ions, so that would be a +1 or a -1 ion, or maybe a +2, -2, or a +2, -1. And then we have the distance, which is going to be the distance between the 2 nuclei of whatever atoms are, I can't really draw that, the distance between the 2 nuclei between whatever atoms are coming together. So our book talks about this as electrostatic force. Okay, and essentially that's the same as the lattice energy, and it's going to increase as the charges increase. So if Q1 and Q2 increase, so Q1 will be the positive charge and Q2 will be the negative charge. And it'll also increase as the radii of our atoms decreases, because then the distance is going to decrease. And if we divide by a smaller number, our overall electrostatic force is going to get higher. This will make a little sense when I do some examples here. I just wanted to point out that the College Board actually calls this Coulomb's law. And so it's exactly the same. You'll see Q1, Q2, and they use radius squared. But we don't really have to do math with either of these equations. And so it's just that the lattice energy is going to be proportional to the charges over the distance or the radius, okay? And so whether we call it electrostatic force or Coulomb's law doesn't matter, but I did want to point out to you that the College Board often uses the word Coulomb's law. So if they say like, explain this using Coulomb's law, make sure you're talking about charge and radius, okay? So let me show you what I mean here. This is just, that is the same thing as electrostatic force. Okay, so arrange NaF, CSI, and CaO in order of increasing lattice energy. This would be an example of the problem that they're going to ask us. Nothing that's going to involve crazy math. So sodium is a +1 ion. Fluorine is a -1 ion. Again, I should really say 1 plus, 1 minus. Cesium and iodine, 1 plus, 1 minus. Calcium and oxygen, 2 plus and 2 minus. So that means I know immediately that calcium oxide has the highest lattice energy, because when I'm thinking about Q1, Q2 over R, since Q1 times Q2 for NAF would be 1 times 1, for CSI, 1 times 1, but for CaO, it's going to be 2 plus 2. Sorry, 2 times 2. And so since calcium oxide has the higher charges, the numerator is going to get larger. So I know calcium oxide is going to have the highest lattice energy. I always look at charges first and see if I can make a differentiation there. Now I have to compare sodium fluoride and cesium iodide. Unfortunately, both of those have the same charges. So I can't just think of the charges because both are +1 and -1. So that means I have to start thinking of the radius. Remember, the smaller the radius, the larger my lattice energy is going to end up being. So I need to figure out which one is smaller, NAF or CSI. To do that, I'm going to look at my periodic table. NAF, CS. Ooh, CS is bigger than NA. I know that from my periodic trends. Oh, and I is bigger than F. I know that from my periodic trends. So CSI is much larger than NAF. Because of that, NAF will have the larger lattice energy, and CSI will have the smallest lattice energy. Oh, can't really write it. Come on. CSI. Again, remember, the smaller the radius, the larger the lattice energy, because we'd be dividing by a smaller number. And I found out that NA and F were both smaller than CS and I. So that's why I put NAF as having a larger lattice energy than CSI. Okay. Let's take a look at another one. Which would you predict to have the greatest lattice energy? MgF2, CaF2, or ZrO2? Well, let's see. Mg2 plus, F is -1, Ca is 2 plus, F is -1. Please notice I'm looking at the charge of the ion, not how many of the ion I have. So F is a -1 ion. Even though I have 2 -1 ions, I'm not counting that as a -2. It's still a -1 ion. So it's the charge of the ion. So magnesium is the +2 ion, fluorine is a -1, calcium +2, -1, so those are the same. Zirconium is a +2, and oxygen is a -2. Oops, I wrote oxygen. So I don't have to do much here because I can just use Q1, Q2 over R. I know that since ZrO2 has the higher magnitudes, +2, -2, ZrO2 is going to have the greatest lattice energy. Now, if I did need to compare magnesium fluoride and calcium fluoride, I would do that based on radius. So let me take a look again at my periodic table. Magnesium is right here. Let me do some erasing. Magnesium's right here. And what was it? Calcium? Yep. Calcium is right here. The fluoride part is the same. So magnesium is smaller than calcium. So that would make magnesium have the higher one. So if I did need to rank these, I would do ZrO2 greatest based on charge, and then magnesium, and then calcium. Again, calcium fluoride had the largest distance, which would mean it actually has the lowest lattice energy. So when it comes to lattice energy, that's pretty much the types of questions that we get. So I know the explanation of it can get kind of like nitty-gritty, especially when we're talking about this stuff here, the stabilization, and like everything being, oh, what's going on? I'm stuck. Okay, so I had to pause and restart here, but hopefully it works out. But what I was saying is that sometimes thinking about lattice energies and lattices can seem very confusing, but really in order to answer the questions that they might ask us, it's really going to be just focusing on this Q1, Q2 over R idea. So that really brings us to the end of ionic bonding, which is awesome. So we can quickly move on to metallic bonding. Remember that metallic bonding is about metals bonding together, and we always use this term sea of electrons. And so a major piece of metallic bonding is that it is different than ionic and covalent bonding in that we use a model of delocalized electrons. So when we look at metallic bonding, we don't use Lewis dot diagrams because Lewis dot diagrams represents electrons as being localized to a specific atom. That means when we talk about Lewis dot diagrams, like if I say, here's the Lewis dot diagram of calcium, I say these two electrons belong to calcium, right? They're localized to a specific atom. But when we look at metallic bonding, we actually don't look at valence electrons being for a specific atom. Instead, we use this sea of electrons model. And so the sea of electrons model have electrons delocalized, meaning that electrons don't belong to a specific atom. They're just in this sea of electrons that could go to any atom. And so it's important to know that metallic bonding doesn't really use Lewis dot diagrams. Instead, it uses this sea of electrons model, which means that valence electrons are not localized to any specific atom. So the way that works is the positive core of the, I said electron. The positive core of the metal is the word that needed to be there. The positive core of the metal is stationary. And when I say positive core of the metal, I mean the nucleus of the metal and its core electrons. That's going to end up being positive because the protons, there will be more protons than there are electrons because we haven't counted the valence electrons yet. So the positive core of the metal, which is the nucleus and the core electrons, are stationary in this model, but the valence electrons are supermobile. And so when we think about metallic bonding, we have some kind of positive core. This is the nucleus plus the core electrons. And then we have all these valence electrons out here that are supermobile. Okay? And them being supermobile gives rise to metallic properties. So because electrons are supermobile in metals, that's why metals are good conductors of heat and electricity. Because all the electrons are supermobile, the valence electrons. That's why metals can be malleable and ductile, because deforming the metal doesn't actually affect this stationary core here. And so when metals bond together to themselves, like I'm talking about like iron bonding to iron to make a sheet of iron, we know that we have this stationary core and these mobile electrons that are forming the sea of electrons. Okay. Now, alloys are something that comes up a lot when we talk about metallic bonding. An alloy is a combination of metals or metals combined with one or more elements. I actually previously thought that alloys were always mixtures of metals, but I learned that alloys are sometimes mixtures of just metals, but sometimes it can be a metal with a non-metal and it's still considered an alloy. So it is a mixture, but it's always a mixture that involves a metal, sometimes another metal, sometimes non-metals. So an alloy is a combination of metals or metals combined with more than one other element. Some examples are steel. You'll notice steel is an element. It's a mixture of iron and carbon as well as other things, but those are the two main components. Bronze is a mixture of copper and tin as well as other elements, but these are the major components. And brass, which of course we did our brass lab, and we learned that brass is a mixture of copper and zinc as well as a bunch of other things. And so these are examples of alloys. Notice bronze and brass are two metals mixed together, but steel is a metal and a non-metal. All of these things are considered alloys. Okay. We have two different types of alloys. We have interstitial alloys, which is when atoms of vastly different radii combine. So an example of an interstitial alloy is steel, which I had mentioned is iron and carbon. So here's a picture of that. The dark ones are the iron atoms, which are actually quite large, especially in comparison to the carbon atoms, which are quite small. So in an interstitial alloy, you'll see that the small carbon atoms actually fit in these spaces in between the iron. And so, first of all, the way alloys are made is, in this case, for example, they would heat iron and they would heat carbon and then they would mix them together, right? And what would end up happening is that the carbon atoms would kind of slide into these spaces, or it says interstices. I'm not sure how to say that word. But it basically slides into these holes between the iron atoms. And this is how the alloy is created. And because the carbon and the iron have very different radii, the carbon is much smaller, we get an interstitial alloy. Okay, an interstitial alloy means that there are a ton of extra bonds. I'll show you where those bonds are coming from, because this carbon is bonding here, and that's going to be covalent bonds, right? Because this is a non-metal and a metal. So there's going to be tons of extra covalent bonding here. And that extra covalent bonding causes the metal lattice to become harder, stronger, and less ductile. So the main reason we make alloys is because they have properties that are different from the metals by themselves, right? Why would we use steel when we could use iron? Well, it's because steel has some properties that we prefer. So when we put the carbon in with the iron to make steel, the steel ends up being harder, stronger, and less ductile than the iron is by itself, which can be super useful, for example, in industry. So interstitial alloys are when two things are put together. They have different radii. The smaller one kind of fits in the spaces between the larger one, and then we get these special properties of them being harder, stronger, and less ductile. Okay, now alternatively, we can have a substitutional alloy, okay, which is when atoms of similar radii combine. And in this process, what happens is the one element actually takes the place of the other element. So here's brass, which is copper and zinc. And we can see that the copper ions that used to be present are now replaced in some places by zinc. I said ions, but I meant atoms. Are replaced by zinc atoms. And so when this substitution happens, notice the spaces are still available. Nothing's happening in the spaces. It's that some copper atoms were replaced by some zinc atoms. That's a substitutional alloy. Obviously, a zinc has substituted in for a copper. Okay. A substitutional alloy, you can really vary the concentrations of the different things, like the concentration of copper to zinc can vary. And if you vary that, you can get different types of properties. And so we might be able to change the strength, the resistance to oxidation or rusting, increase or decrease the conductivity, increase or decrease the melting point, and of course, change the price. So one example of a substitutional alloy is 14 karat gold, which is a mixture of silver and gold. By substituting in some silver for gold atoms, you can reduce the price, but you still get the properties that you want. So there are actually two other types of alloys, but those are not covered in our EP curriculum, so I'm going to not talk about them today. But interstitial and substitutional alloys are two ways that metals bond together to form mixtures. This picture I just thought was helpful. Here's a pure metal. So when metals bond together, it's just going to look like this nice solid here. And again, remember we use the sea of electrons model. So we assume that there's a stationary core and then valence electrons moving around here. Okay, on each of these atoms, that's going to be a pure metal. A substitutional alloy will be when we have our metal, but we have replaced the metal, some of the atoms, with another atom here. Okay, now this picture shows a little bit of a difference in radius, but not a huge difference in radius. And then an interstitial alloy is when we have two items of a different radii, and you can see that the smaller one fits in the spaces. So that brings us to the end of metallic bonding. And then I just reviewed everything from this PowerPoint, and I realized we have two topics that I didn't cover in covalent bonding that are actually pretty important. So one of them is internuclear distance. And so this is kind of like backtracking a little bit to covalent bonding. We talked about the length of covalent bonds, and we said that, we can look up the length of different bonds, and we know that double or triple bonds are smaller than single bonds. But it's important to know where they get the bond length from. The bond length is based on the balance of two forces. The repulsive force, the nuclei, which are both positive, are going to repel each other, and the attractive force, which is the protons of one atom attracting the electrons of another atom. So what am I talking about there? I mean, if I have like a hydrogen atom, there's the nucleus of a hydrogen atom. It's a +1 charge, and here's an electron. If a hydrogen was going to bond to another hydrogen, that would be a covalent bond. Okay, there would be a couple forces at play. This positive nucleus right here and this positive nucleus right here are actually going to repel each other, right? Push away from each other because they're like charges. But on the flip side, this positive proton right here is actually going to attract this negative electron. And the same way here, this positive proton is going to attract this negative electron. So we have two competing forces. And so at what point will the attractive force and the repulsive force balance out to actually allow this to bond together is the question. And so we know that a bond is going to form when the potential energy of the bond is at its minimum level. Remember, nature is inherently lazy, so things happen at the lowest possible energy. Okay, this lowest possible energy is going to happen, like I said, when the repulsive force and the attractive force are balanced. So let's take a look at this picture right here. On the x-axis, we have the internuclear distance, basically the distance from nucleus to nucleus of two atoms. Okay, that is going to actually be the bond length, right? Once the atoms bond, this distance is what we call the bond length. Okay, so that's going to be the internuclear distance, and that's on the x-axis. The potential energy is on the y-axis. If you need to look at a graph like this and determine the bond length, this is for an H2 molecule here. The bond length is going to be whenever the potential energy is actually the lowest. This right here is going to be when the bond forms. And that bond length is going to be this distance right here. Okay, that bond length is going to be this distance right here. And so that would be, in this case, it's in picometers, and so there would be some kind of number like 74 picometers is the bond length of hydrogen. You can notice that up here, the potential energy is super high because the H and the H are so close to each other that the protons in the nucleus are actually repelling each other. So there's a lot of repulsion happening here, and so the potential energy is really high. On the flip side, here, the atoms have gotten so far apart that basically they're not attracted to each other at all, because there's no way the nucleus of this guy can get attracted to the electron of that guy. So we have basically a potential energy of 0 because they're not attracted to each other at all. So this is going to be the point at which the bond forms when the potential energy is at its lowest, and that will be a negative value. But remember, with energies, we do have those negative values. So we want the potential energy to be absolutely the lowest, and when it is at its lowest, that is when the bond will form. From this diagram, we can get the bond length, which we already talked about, but we can also get the bond energy. So this value right here is actually the bond energy, which we talked about as well. And we can look up charts of bond energies, but how do they actually get those? By measuring this data right here and making this kind of chart. So this chart is going to be really important. I have seen many AP problems use a chart like this. Again, let's just review. We have the potential energy on the y-axis. We have the internuclear distance on the x-axis. We are going to always locate the lowest point on this graph. That's going to be when the potential energy is the lowest. That's going to be when the attractive forces and the repulsive forces have balanced each other out. And this is when the bond is actually going to form. When the bond forms, we can measure the x-axis to get the length of that bond, and we can measure the y-axis to get the bond energy. Of course, if atoms are too close to each other, they will repel and therefore not bond together. And if atoms are too far apart from each other, they won't be attracted and therefore not bond with each other. Okay, so to give you some more information on that, I actually found this video here that I'd love for us to watch. So I think I can get it started.
In a previous video, we began to think about potential energy as a function of internuclear distance for diatomic molecules. What do I mean by diatomic molecules? Well, we looked at molecular hydrogen, which is just, or H2, which is just two hydrogens covalently bonded to each other. And at standard temperature and pressure, they would naturally, the distance between the two nuclei would be based on where there is the lowest potential energy. And if you were to squeeze them together, you would have to put energy into the system and have a higher potential energy. Or if you were to pull them apart, you would have to put energy into the system and have a higher potential energy. What I want to do in this video is do a little bit of a worked example. Over here, I have three potential energies as a function of internuclear distance graphs. And what I'm going to tell you is one of these is molecular hydrogen. One of these is molecular nitrogen, or diatomic nitrogen, N2, and one of these is diatomic oxygen. And what I want you to think about, pause this video, is which graph is the potential energy as a function of internuclear distance for each of these diatomic molecules. And I'll give you a hint. Look at the low point in potential energy. The low point in potential energy is what you would typically observe that diatomic molecules' internuclear distance to be at standard temperature and pressure. And this distance right over here is going to be a function of two things. It's going to be a function of how small the atoms actually are, how small their radii are. So smaller atoms are in general going to have a shorter, stable internuclear distance. But the other thing to think about is the bond order between these atoms. And I'll give you a little bit of a hint. Diatomic hydrogen, you just have a single covalent bond. For diatomic nitrogen, it is a triple bond. And for diatomic oxygen, it is a double bond. So the higher order the bond, that will also bring the two atoms closer together. And it also makes it have a higher bond energy, the energy required to separate the atoms. Remember, we talked about it in the previous video. This right over here is the bond energy. And so with that said, pause the video and try to figure it out. Which of these is the graphs of H2, which is N2, and which is O2? So let's first just think about it in terms of bond energy. If you look at it, the single bond, double bond, triple bond here, you would expect the highest order bond here to have the highest bond energy. And the highest bond energy is this salmon colored one right over here. So just based on that, I would say that this is a good candidate for N2. So this one right over here, this looks like diatomic nitrogen to me. Then the next highest bond energy, if you look at it carefully, it looks like this purple one right over here. And so just based on bond order, I would say this is a good candidate for O2. And then the lowest bond energy is this one right over here. And so just based on the bond order here, it's just a single covalent bond, this looks like a good candidate for diatomic hydrogen. But let's also think about the radii of these atoms. If we get a periodic table of elements here, we can see that hydrogen only has one electron in that first shell. And so it's going to be the smallest. So that makes sense over here, that your distance where you have the lowest potential energy is shortest for the diatomic molecule that's made up of the smallest atoms. But then when you look at the other two, something interesting happens. Remember, your radius for an atom increases as you go down a column, but as you go to the right on a row, your radius decreases because you're adding more and more electrons to the same shell, but the Coulomb forces are increasing between that outermost shell and your nucleus. And so if you just look at that trend, as you go from nitrogen to oxygen, you would actually expect your atomic radius to get a little bit smaller. They're right next to each other. They might be close, but you say, okay, oxygen, you have one extra electron in that same second shell. Maybe it's going to be a little bit smaller. So if you were to base things just on that, you'd say, all right, well, the internuclear distance for this salmon-colored one is a little bit shorter. Maybe that one is oxygen, and maybe this one is nitrogen. But they would be close, and I would say in general, the bond order would trump things. And the bond order, because you see this high bond energy, that's the biggest giveaway that this is going to be the higher bond order diatomic molecule, or N2. They're close in atomic radius, but this is what makes all of the difference, and we'll take those two nitrogen atoms and squeeze them together just a little bit more, even though they might be a little bit bigger. And so I feel pretty good with this labeling.
All right, I just got to figure out how to get back here.
If you were to find a pure sample.
Okay, so I thought that was a really great video just to show how we can compare different molecules and their internuclear distance, which would be their bond length, as well as their bond energy. And I do think that being able to do that comparison is going to be important, and it actually comes up in your homework tonight. So next, let's see if I can get to the next section here. The second piece, that was internuclear distance. The second piece that I hadn't talked about is something called valence bond theory. Then this is actually something that I haven't covered in the past, but it does show up on the curriculum for AP, so I wanted to at least mention it. To be honest, in my experience, there haven't been very many questions about valence bond theory, but since this is kind of a different era, I just want to make sure that we cover all of our bases. And so again, we're still talking about covalent bonding. We know that the VSEPR theory, that was the valence shell electron pair repulsion theory. I have it spelled wrong actually right here. Valence shell electron pair repulsion theory allows us to easily predict the molecular geometry of a molecule. So we can say it's tetrahedral or it's bent or whatever. We use the Lewis theory or Lewis dot diagrams to show that covalent bonding occurs when atoms share electrons because the sharing concentrates the electron density between the nuclei. That's a complicated way of saying that when they share electrons, everybody feels like they have 8, right? Like that's the complicated way of saying that. So we've used the VSEPR theory and the Lewis theory. The valence bond theory suggests that we should visualize the buildup of electron density between two nuclei as occurring when atomic orbitals are overlapping with each other. So this idea that electrons get shared, not just because everybody wants 8, but electrons get shared because orbitals actually overlap with each other. So to understand that, we have to know a little bit about orbitals. Oh, sorry, this last piece here. It allows 2 electrons of opposite spin, that means 1 up arrow, 1 down arrow, to share the space between the nuclei, and that's why a covalent bond would form. So instead of just saying covalent bonds form because when atoms share electrons, they all get to feel like they have 8 or achieve that noble gas-like configuration, the valence bond theory says that if orbitals of different atoms overlap, then electrons that spin in opposite directions can share the same space, and that's why a covalent bond forms. So to understand that a little bit, we just need to know a little bit about orbitals. So we know that we have 4 orbitals, S, P, D, and F. And roughly they have these shapes. A spherical shape for an S orbital, a P orbital is this dumbbell shape, the D orbital is this double dumbbell shape, and the F orbital has this like flower shape. If you were to stack all of these right on top of each other, it would make this sphere that would make the electron cloud. Okay. Now, that was a little bit of a simplified version. Here we can see an s orbital. Remember, things are 3D, so we're trying to look at them on 3 axes. S orbital is spherical. The p orbital, remember when we draw a p orbital, we draw 3 lines like 2p, right? Like this, with 3 lines. Each of those lines represents one of these axes. So this would be 1 line, this would be 1 line, this would be 1 line. In the same way, the d orbital, which has that double dumbbell shape plus that extra ring we're seeing on one of them, represents the 5 lines that we see of d, right? 1, 2, 3, 4, 5. Okay, so it's important to remember that orbitals have shapes and orbitals are 3-dimensional. Okay, now what happens here is, here's HCl. Hydrogen is just 1s1. Right? So here's an s orbital that's spherical, and there's 1 electron on it. Chlorine, of course, is 1s2, 2s2, 2p6. And here is like the 6th electron in that p orbital. Okay, and so this is the valence electron in the p orbital, the one that isn't paired. And what ends up happening is this s and this p end up overlapping with each other. And when they overlap with each other, they bond. And so that's the idea of valence bond theory, is that orbitals are overlapping. Remember that we have something called sigma bonds and pi bonds. Sigma bonds are the single bonds, pi bonds are the multiple bonds. So remember that sigma bonds are single bonds, and they occur when there's an overlap of 2 s orbitals, an s and a p orbital, or 2 p orbitals. So I just showed you an example of a sigma bond, a single bond that would form between H and Cl when an s orbital overlaps with a p orbital. Here's an example now of 2 s orbitals overlapping. So this is the s orbital, I should actually label it here, the s orbital of one H and the s orbital of another H. This is the valence electron and the valence electron. They overlap right here, and that would cause a sigma bond. Here's Cl2, okay? Remember Cl, 1s2, 2s2, 2p6, 3s2, 3p6. I might have said that wrong earlier in the video. I think I stopped at 2p6. Oh gosh, I actually said it wrong. Let me go back to that one because I said 6, but to be clear, this is 1s2, 2s2, 2p6, 3s2, 3p5, hence the unpaired electron. So this is actually the 5th electron of chlorine. Okay, it's actually the 5th electron of chlorine that's unpaired, and that's the one that overlaps. So the overlapping part I explained properly. I was just saying the wrong numbers there. Sorry about that. So anyway, back to our third example. This was one where 2 s orbitals overlapped. So if we want to see 2 p orbitals overlap, that would be if we made Cl2. So now we have the correct electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5. And we can see that that 5th unpaired electron of both chlorines end up overlapping. So this is the paired electrons like these two. This is the paired electrons like these two. And then the 2 that I have circled are the unpaired electron there. And so that would be a sigma bond when 2 p orbitals overlap. It's also represented like this if we cleaned it up a little bit, where this is the unpaired electron and this is the unpaired electron, and then they overlap there. Okay. Pi bonds, which are going to be the multiple bonds, remember, occur when there's an overlap of 2 p orbitals. Now, I just showed you an example of 2 p orbitals overlapping, forming a sigma bond. But also when 2 p orbitals overlap, it is possible to form a pi bond. And that's going to occur perpendicular to the sigma bond. And so when I'm talking about the planes, I'm just reminding you here that like if the nucleus is here, right, with the s orbital, then on the same plane is like this guy, right? So if a p and a p overlap there, that's going to end up being a sigma bond. But if a p and a p overlap, for example, here, which is perpendicular to that, then it ends up being a pi bond, okay? Also, I hope you guys can hear it storming so loud outside right now. So pi bonds occur when there's an overlap of two p orbitals, and it's always perpendicular. So here's an example. It's an N2 molecule. Now, if you are like me, I was really struggling to understand this drawing right over here. I understand that nitrogen is 1s2, 2s2, 2p6, but I can't figure out what's happening here, right? So here's a quick video that explains it a little bit. Let's go ahead and take a look. Hopefully. We have an ad.
Okay, welcome to ilectureonline, and here we're going to take a look at a double pi bond example. That double pi bond will exist when you have a molecule like nitrogen, not N3, and 2. I thought about the 3 when I was thinking about a triple bond, but no, it's actually the N2 molecule. It's a nitrogen gas molecule. It comes about when you take 2 nitrogen atoms, you join them together, and you form a molecule like that with a triple bond, and there's the Lewis structure of that bond. Notice that each nitrogen still has 1 lone electron pair remaining. So how does a bond like that form, and what does it look like, and why are there pi bonds as well as the singular sigma bonds? So let's see in just a moment. Nitrogen has 2 electrons in the 1s orbital, has 2 electrons in the 2s orbital, but it only has 3 electrons in the 2p orbitals, which means there's only 1 electron in each, which means that nitrogen is very likely to form as many as 3 bonds. So how does that work? Well, since nitrogen has 3 p orbitals, it has a p orbital in the z direction, a p orbital in the y direction, and a p orbital in and out of the board in the x direction. So here we have 2 nitrogen atoms like that. And the 2 p orbitals that are sticking towards each other in the y direction, they will overlap. The single electron in the orbitals will share that space for a significant amount of the time, and they will be in phase within that space, creating that negatively charged region, pulling the 2 nitrogens together. What about the other 2 p orbitals, the one in the z direction and the one in the x direction? Well, what happens is the one in the z direction will come and bend towards like this and form reshape an orbital, so to speak, in a way, joining the 2 orbitals together like that, forming a region where the 2 electrons can exist. So I'll draw 1 electron there and 1 electron there. So that would be 1 electron from this nitrogen and 1 electron from that nitrogen. And so we form these bonds like that around, shaped like that. And so this is a single pi bond, and that would be accomplished by joining the pz orbitals together. But what about the py orbitals? Oh no, there we have those already. What about the px orbitals? They have a single electron in each nitrogen as well, and so they will want to form bonds, and they're going to form bonds by bending in this direction, one in front of the board, one behind the board. So how do I draw that? Well, not easily, but let me try. So I'm going to represent the x orbital bending over and forming a bond like this. And this would be the bond coming out of the board, and then we have the x orbital on the other side joining together like this and forming a bond behind the board. So I'll put an electron in each, and just to try and help illustrate what that looks like, I got my little magnets out here, and there you go. Here's the 2 nitrogen nuclei. We have the single.
Okay, we can go ahead and stop there. I think we're right here. So that just kind of helped to understand how those pi bonds are formed. Now, to be honest, I find valence bond theory quite confusing. And I do think it's a little bit of a stretch. Like, I really haven't seen very many questions on our AP exam about valence bond theory, but like I said, they mentioned it in the curriculum. So I just wanted to at least give you a little bit exposure to it, but it's not something that I would stress about too much if you're finding it confusing. The last piece is basically valence bond theory is the theory behind hybridization. So you guys do know how to answer this question, which is related to valence bond theory. What is the hybridization SP? Because SP, two things, two, right? SP2, the steric number 3. We talked about this last time. So you guys know how to do this. The valence bond theory is actually the basis of what this means. But I believe that hybridization is not something that we get asked about beyond needing to label it as SP or SP2. And so I think we can go ahead and stop there with that. Again, if you were to pursue chemistry in college, you'd learn more about this and then actually move on to something called molecular orbital theory, I believe it's called, and that kind of continues in this vein. But I just wanted to make sure you had some exposure to that. So this is a super long video, but now we have finished Unit 2 according to the College Board curriculum. So I'm just trying to make sure that we have covered everything that they're telling us that will be on our AP exam this year. So I'm not going to go through all of this, but I just want to show you that I did check the way the curriculum is laid out. The College Board divides everything into units, and you know that there are 9 units, and we're going to be covered on 7 of them. Each unit has things called enduring understandings. Under each enduring understanding, there's a thing called learning objectives, and under each learning objective, there's the essential knowledge, things that you guys should know. And so here I just have all of those things listed, and I went through each one of them to ensure that we covered all of them. And we did. This is how I went back to add the 2 things that we had left off. And so, of course, I encourage you to look up on the website, or I can share this PowerPoint with you as well. And you can look through these things to just for yourself make sure that you know how to do all of these things. So that brings us to, let's keep this. That brings us to the end of our video. I hope that you guys have a lovely day. I look forward to talking to you guys tomorrow and seeing you as well on Zoom. Have a great day. Bye.